So this video is going to be about speeding up simulations with that are done with gpvdm. There's quite a few people using the model now, and I thought it'd be quite useful to make a video on effectively how you can run your simulations faster and sort of optimize the speed at which they run, because if you're running a lot of simulations, obviously it's good if they go faster. It's going to be a slightly different video to most of the videos I make about gpvdm, because it's going to have a little bit of maths content, and we're going to talk about some of the sort of fundamentals of the model, and then once you understand those, we can talk about how to speed it up. So let's talk about before we talk about speeding things up, let's talk about some of the foundations of the model. So to calculate or to account for effectively charge transport in the device, we solve the basic drift diffusion equations along with Poisson's equation. So Poisson's equation, or Gauss's law, is here. We have the electron and hole driving terms, so those are just the drift diffusion equations, the continuity equations, and those are solved effectively on a finite difference mesh across the device, so that there's a picture of the device, and we can basically account for charge movement from left to the right across the device in both the LUMO and the HOMO. Now that's all very well because it accounts for effectively charge transport, but there's also charge trapping and recombination that is very important in organic devices and many other types of devices. So to account for this, we solve effectively the Shockley-Reed-Hall recombination model. Now it's usual when you do when you're trying to sort of, account for Shockley-Reed-Hall recombination to sort of boil the equations down into one simple equation, sort of which assumes sort of steady state, and it's quite easy to implement in the model. But because we want to solve the equations in time domain, we have to actually fully solve all the Shockley-Reed-Hall rate equations at each mesh point on the finite difference mesh within the device. So under each mesh point, we effectively have this picture shown. So EE is effectively the electron, the mobility level, and EH is the whole mobility level, so the LUMO edge and the HOMO edge. The red triangles sort of red triangles descending from the LUMO account for the LUMO trap states, and the blue triangle descending from the HOMO edge accounts for the HOMO trap states, and the sort of the parabolas on the top and the bottom represent effectively parabolic bands. So for each one of these squares within these triangles, these are individual traps, and for each one of those we need to solve the full Shockley-Reed-Hall capture and escape rate equation, which is given there on the top right. And then once we've done that, so that accounts for basically capture and escape for electrons from the trap, and capture and escape for holes from the trap. And once we've done this for each trap level, then we can sort of calculate the recombination rates and the trapping rates and things like that. So if we solve this model in energy space at each point in the device in position space, what we can do is we can calculate effectively the density of charge carriers at any place in the device in both position space, so position space along the bottom of the device, and energy space up the left hand side. So what we end up with is effectively a map of charge density within the device as a function of energy and position, which is effectively what makes this model special, because it resolves the carriers in energy and position space, which means you can do all types of interesting transient calculations without any approximations. Now, how do we solve these equations? That's really what I'm trying to get at. So all these equations that I've just mentioned are solved with Newton's method, and there's a picture of Newton. Now, I think Newton's method is a very, very powerful method used to solve when used to solve semiconductor equations, and I think it's sort of so I think raw Newton's method is probably one of the most efficient methods to solve this type of equation set. Yeah. So I've sort of cannibalized this for some lecture notes I had. So to sort of understand Newton's method, let's think about this problem. If I gave you this equation to solve, so 0 equals x to the minus 3, x to the minus 4, how would you solve it? Well, just looking at this from sort of standard maths, the answer would be plus 3 and plus 40, because that's obviously when the equation is equal to 0. So there we go, plus 3 and plus 40. Now, another way to sort of look at this problem is to say, well, okay, rather than having this equation equal to 0 there, let's say f of x equals then x minus 3 times x minus 40. And what we can do is we can vary x and look at f of x. So there's a graph of it. So we're varying x and we're looking at f of x. And quite clearly, the points where our equations are solved are at x equals 3 and x equals 40. And these are called the roots of the equation. So this sort of way of writing equations as a sort of an error function, effectively. So f of x is an error function. And then you play with the value of x until you get the answer to the equation. It's very powerful when it comes to solving these semiconductor equations. So effectively we replace this with the semiconductor equations, and x wouldn't be x, it would be say 5 for the potential, or f of n, which is the Fermi level for electrons, or the Fermi level for the holes. And we sort of play with the values of these variables until we hit f of x is equal to 0. So sticking with this equation for the time being, well, this will work with any type of equation. So picking a different equation now to sort of understand Newton's method, the general principle with Newton's method is basically you write out your equation you're interested in. So here I've made some simple algebraic equation, and you could so this would be in gpvdm the semiconductor equations. And then what you do is you effectively differentiate this equation with respect to x, so the variable you're trying to solve for, and we get f of x dashed. So, and then what we have to do is we have to guess a value of x. You know, you just literally have to guess any old value. And my guess is, say, 10. Now, if we look at this equation, 10 is a really bad guess, because we can go 10 squared is 100 plus 10 times 10 is 100 minus 3 is 197, which is quite obviously wrong. But never mind, let's stick with this guess of 10. So what we do is we evaluate f of x at 10. We evaluate the differential of f of x, so f of x dash at, say, 10, and we get these values. And then this is Newton's method. What we do is we stick these values we've just got into the right-hand side of this equation, and the left-hand side is a better guess for x. So we stick x is 10 in there, that's our really bad guess. We stick f of 10 in there, which is a better guess, which is basically the error function. So f is our error function. We stick the differential at our really bad guess in there. Then we calculate x plus 1, which is our better guess of x, and it's 3.433, which is a better guess. So then what we do is repeat the procedure. So we stick this better guess back in here. So x is 3.433 because that's what Newton's method told us. F of 3.433 is 43.11, and you see this error function is basically getting closer to the answer, so it's getting closer to 0. Our better guess of f of dashed is that. We get another better approximation to x, and the process basically continues and continues and continues until we get our basically an answer which converges where f of x is 0, and this means we've solved our equations. So effectively, if I just go back, effectively all this method is a complicated way, and a very efficient way, it's worth saying, of effectively finding out where our equation hits, so the x-axis, so x would, in this case, would be x equals 3 or x equals 40. So let's go back, let's go forward. So that's effectively the procedure. So firstly, you write your equation down, you write the differential of the equation down, you guess x, and then you guess a value for x, and then you iterate around this Newton equation until f of x is basically 0, and you converge on your answer. So I've sort of implemented this in Matlab here. So here we've got our sort of a for loop that counts from 1 to 10. Bit of the equation, the differential equation, which is dy, and I'm printing out effectively the value or the root that we're looking for, and then the value of f of x, which is the error. And this is the output on the right hand side. So in the left, this is my mouse work. In the left column, this is the value of the root we're looking for. So our first guess is 10, then it's 3.43, then it goes down to 0.87, then this value, and then within about 4 guesses we've come down to 0.29, 0.29, 0.29, and this here is the error function. So this was our first error we got, which was 197. It's clearly way out. 43 is a better error, 6 is a better error, 0.3 is a better error, and then we're into sort of very quickly it decays down to 0. And what you'll notice is this is effectively called superlinear, so it's a superlinear decay of the error. So we've got 3 decimal places, 2 decimal places, 1 decimal place, 0.1 decimal places, 0.0001 decimal place, and then no error. So it's a very efficient way to find, Newton's method is a very efficient way to find roots of this equation. So this is how this relates to the model. Basically, we write our semiconductor equations in matrix form. So J is effectively the differential of all those equations I talked about previously. It's a drift diffusion equation and all that. Delta X is our better guess of all of our variables. So these are matrices. So this will be all the values of, so a better guess of field across the whole device, a better guess the Fermi level across the whole device for electrons and holes, a better guess the Fermi levels in all the traps, equals, and then minus, and this is our error function. And what we do is we basically calculate this, so it doesn't matter exactly how, but we just calculate an update, which is our improved guess. We add our improved guess to X, just as we were doing before, and we get a better guess of basically the potentials and the Fermi levels and all of that, and we stick this X back in here, and then we iterate again and again and again until we get an answer, until we get f of x is about 0. So the important thing to note about this is basically it's an iterative process to solving these equations. F of x there is important. This is basically the function we're trying to minimize, so this represents the error in all of our device equations that we basically want to be 0. And another important takeaway message is that the better the guess you can get, the better the initial guess, the closer you can get to the solution initially, the quicker your equations will converge. So with that said, let's go and play with the model. So let's fire at the model and let's make a new simulation. Now what I'm going to do in this one is I'm going to make a 2D device simulation. So we're going to make an OFET simulation, and I'm going to save it on my desktop in a file called sim. Now this is so we're looking, so for a start this is running on a laptop. It's not a super powerful computer, it's an i7, but it's a few years old, so you know it's not, this isn't a nice workstation at all. So we've got a 2D OFET simulation. So if we just run that simulation straight out of the box now and just look how long it takes. So we're about 10 seconds past. About 15 seconds or so. So I'm not going to time this accurately, but you'll have a feel for what's going on. So before we dive into the math, I'll try and give you some now super easy tips to speed up the simulation. This button here, so one thing that's really slow in these simulations is dumping to disk. So whenever you use a hard disk computer, it's just a very slow process and it will slow down your simulation immensely. So if you want a really fast simulation, don't dump lots of data to disk, and to stop data being dumped you basically press this button, which will minimize the amount of data that's dumped to disk. So if you run this again, it'll probably be a little bit faster. So it's probably running a bit faster now. Now what this does is, if you look in the configure window and under output files, there's all these options here that are basically various dump parameters. So it'll dump, you know, many of the output files you can turn on or off whether or not you want them. So for example, dumping dynamic will dump sort of lots of dynamic time domain data. You might not always want that, so you can turn that off and on, and you can play with what gets spat out. And if you turn this back on, then it's effectively it effectively turns, well, this button here effectively turns on and off all these options en masse. Okay, so now let's look at the numerics of the model. So firstly, let's turn on So this was the output we've just got from our simulation. Now what this hides is basically the iterative convergence of the solver. So let's turn that on so we can see what's happening. Now I think the option is print Newton error. Let's also write Newton's convergence to disk. So now when we run this, rather than just printing out one line for each voltage that it solves of the transistor, if we run it, whoops, it's going to be a bit slower. Okay, let's go down. So now this is effectively the first. So what we're looking at here is this is the output from the first simulation step. Now when the model kicks off, it doesn't know anything about the device. It doesn't have any good guess at all to the set of equations we're solving. So it's very, very far from a solution. It doesn't know what the potential should be. It doesn't know what the Fermi levels should be, and we can provide it with some type of guess, but it's never a very good guess. So this first step in the convergence of the solver, or solving these equations, takes excuse me, let me just have a drink of water. Always takes quite a long time. So here we've got Kerr error, which is current error, and the error is very, very big. So it's 1 to the 15. And then as the solver works on the problem, you can see the error drops off and drops off and drops off, and after quite a while we start to get some very low numbers, 1, so errors of 1. So we've dropped 15 orders of magnitude in terms of error, and then very quickly we hit round about 1 to the minus 7, 1 to the minus 8, 1 to the minus 9. So we've dropped, maybe 20 orders of magnitude in terms of error. And basically, when the model's giving you errors of -9, -8, it means the equations are basically solved. Now, the first iteration is special, which is what we're looking at here, in that we don't let Newton's method converge very quickly. I probably won't talk about this now, actually, but the first step's special in that effectively Newton's method is very constrained, and because it's because the solution is such a long way from the answer, we don't let Newton's method take full Newton steps. We don't let it to basically jump to the answer. We sort of pull it back a bit like a dog on a lead, to make sure it sort of converges slowly to the answer, which means it effectively reduces its chance of crashing. So I'll talk about that in a minute. And also on this first step, we let it have a lot of iterations, let it have a real good go at solving those equations, because obviously it's very far from the answer. So generally speaking, I'll give it about 1,000 steps on the first go. So now it's guessed the first sort of the equilibrium condition, so in the dark at 0 volts, and then effectively, where are we? I think it's doing it. So then after we've done that, effectively, basically, we start solving for various voltages. So this is a voltage of 0 volts, and you see we go from an error of 4 to an error of -10 very, very quickly, because we're quite close to the solution already. And then here, 0.1 volts, we've moved a little bit away from the solution we've already got to 0.01 volts, and very quickly we get to the correct answer. Very, very quickly we reduce the error, and we're getting basically its answers at various voltages. So remember, this is in 2D. This isn't just in 1D, and it's got all the traps and everything it's solving as well. So within a few, if we get to the bottom, with a few, very, very quick convergence. Now, what's interesting is to look at a file called Convergence. So I'm going to look at this in GNU plot, and you can look at it in Excel or whatever you want. It's just literally, if we look at, it's called Converge. If you look at it, it's just literally a column of numbers, and every time you run the solver, it spits out one of these numbers. So you can look at basically error as a function of whatever simulation you're doing. So if we plot this, in fact we'll plot it with lines, you get a graph that looks like this. And if we plot it on a log scale, that looks funny. Where's the simulation? Ah, yes. So I was in the wrong directory. Right, here we go. So this is effectively the error as a function of all the simulation steps. So this first sort of wander down, it takes quite a few steps, is effectively the initial guess of the simulation. And you see we quickly arrive at effectively an answer, but the solver doesn't end. It continues for 1,000 steps or so, and then we get into this and then if we zoom in here, these steps here are basically every time we increase. So every time we go up a voltage step, so we might have gone from 0.1 to 0.2 volts here, the error in simulation goes up because we've changed the voltage and the answer is now wrong, and then the error drops back down again, and it keeps going like this. So what we can do, and this is effectively that f of x I was talking about previously, so this is f of x, so the error function of all the equations. So we can have a go at speeding up this equation by tuning some parameters in the model. So if we go into configure and we go into the solver configuration, we can play with these parameters. So the first thing we can play with is, well, we had 1,000 steps here for this solver to run, and we can think, well, is that, it's clearly reached a sort of zero here, so this is sort of many orders of magnitude, it's like 10 to minus 9 or something, so this is effectively numerical noise. So do we need to keep running the solver for another, say this is 400 and this is 1,000, so another 600 iterations when we've converged already? The answer is no. So let's reduce the maximum number of steps for the first iteration. So let's reduce it from 1,000 to say 600. Let's go for 600. So we should have knocked off all of these iterations from the model. So let's run it again. Oh, it's not updating for me. So now if we replot this graph, all these should have disappeared, and each one of these represents significant amounts of computational time. So there we go. Now the other thing we can do to sort of, so we've knocked off, maybe 20% of simulation length just by realizing that we just sort of effectively the solver's reached convergence early, so let's just terminate. The other thing we can do is we can, if we go into here, well, this defines when. So this desired electrical solver error first step. So if we put the cursor here, we can see this value down here by looking at the bottom left. So down here, this value here on the y-axis is about 1 to the minus 7, and that looks basically converged for me. That 1 to the minus 7 looks fairly converged. So rather than trying to continue to reach 1 to the minus 9, let's just end it at 1 to the minus 7, and let's run it again. So just running it. So that was slightly quicker. So let's replot this graph, and you see we've again knocked off some extra computational time. The other thing we can do is change electrical clamping. So clamping in an electrical model is basically the proportion of a Newton step that you're allowed to take. So if let's go down. If in this example we looked at earlier, let's look at this one. So we're trying to calculate d of x effectively, and this updates the variables. Now a full Newton step would basically just effectively so divide both sides by j, and it'd be like that, and then and we'll be calculating d of x, which shall update the Newton method. So this is the sort of the improvement or the change in each variable. So if imagine we're guessing a value of phi, it's sort of the update to phi to try and get it closer to the solution. So generally speaking, these solvers, you clamp d of x to not allow Newton to update the full step. So for example, if Newton's method says I want to update a variable by a value of 0.5, you say, well, hang on a minute, that's quite big, let's update it by only say 0.1. And what this does, it sort of slows down convergence, but it means you've got less chance of your solver sort of jumping off into some place that it might crash. So if you think about it in terms of this curve here, Newton's method would sort of roll down this curve to this answer here, but if you take massive Newton steps, it could sort of end up, you know, x equals 10,000. So the idea of clamping is sort of reduce the Newton step and don't let it to go into crazy places. So here we've got, for the first step, we've got a clamp of 0.1. Now that's quite small. 1 is about normal, 0.1 is quite small. I put it as 0.1 to sort of make sure we converge nice and slowly on the first solution. But maybe we can get away with a slightly bigger one. So let's change it to 0.2 and rerun the simulation. And just look at this convergence and see what happens. Okay, so that was actually a bit quicker. So let's refresh this, and can you see it's got much sharper descent. The disadvantage of reducing this or increasing the allowed Newton step is that it could crash more easily, but this looks as if it worked, so let's run it with 0.3, run it again. Okay, and effectively it's shortening this first step. Okay, so let's go back to the model. So that sort of played with the first step. I wonder if we can this, you see that this might crash it now if we increase the steps too much. Let's go up to 0.7 and see what happens. Yeah, so we got away with that. So depending on the structure you're running, you know, often I run it. The input files I distribute with the model are quite sort of conservative guesses for these steps. But you know, if you're playing with one structure, you can probably get away with slightly larger values. So that was of interest. So let's now look at these steps here. So this actually looks to be running quite well. Let's look at this. So various parameters here are the minimum solve error. So this is the error we want on our simulations, basically for all the other steps but the first step. The minimum number of Newton iterations. So this is the number of times the solver must run before it's allowed to exit. And this is useful because sometimes the solver can find false minima. So you say, well, you must run for 5 iterations, and then hopefully that will come over any false minima that it can find. What else do we have in here? So maximum electrical iterations, so 100, and the electrical clamp is 1. So what we could try to do is we could try to be brave and increase the electrical clamp of all the iterations but the first one to 2. So let's try that. It might not end happily, but let's see. So let's look at the total number of iterations we had. So that's 900. We reduced it by 100, and you should be able to see effectively these curves are getting a bit steeper. So that was quite handy. What else? So you can play with this sort of minimum number of iterations. So if for example, so where's the right, so if we set this to 10, the minimum number of iterations, and then run the solver again, so you can see it's basically forcing the model to run a few more times. So what happens is effectively the model gets to the bottom, and then it sort of bumbles along the bottom for a little while because I'm forcing it to run those 10 iterations. So really you don't want it to look like this, you want it to look how it looked before. So I'll set this back to 6 and we won't be wasting time at the bottom. Well, actually we could decrease this to say 2 and see what happens. Yeah, so that's looking fairly optimized to me. So I don't know how long it, so did we say it was 15 seconds before? So let's run this now. So the time on the clock is, we'll say it 10. So that took about 8 seconds. So we've sort of really cut off time from the simulation. And what this means is effectively what you can do is we can now up the number of mesh points to say 50 or some larger number like that. And if we run the model now with a sort of optimized Newton-Solver configuration, and also actually let's terminate this. Let's turn off all the dumping to disk, run it again. So we clearly boost the number of mesh points considerably here, but this will enable us to tackle harder problems. So this will quite clearly take more time. Actually, let's not do that. But okay, so I think that was really it in terms of speeding up. So I'll put this back to 20. So I think that was really it in terms of speeding up gpvdm simulations. So the key things to look at are effectively turn off as much output as you can to disk, optimize the first step of the simulation, then try and play with these parameters, which is effectively the electrical clamp and the minimum error and the sort of the minimum number of iterations it's allowed to do, and try and bring the number of iteration steps, so this graph back, try and shrink this graph right back, and you'll get some quite good performance out of the solver. So 2D solutions within 8 seconds or so. So that's it. I hope this was some use. Thanks for listening, and yeah, that's it.